Taylor series. You would have heard this term Taylor series many times in many places. Maybe in your college lecture, your professor would have directly written one particular polynomial, which he would have told is Taylor series, and then he would have claimed that that polynomial is approximation of some particular function. I'm sure you would have got perplexed on what is this particular series. That is, how this series is able to approximate some particular function. This is what we are going to clarify in this particular lecture. We are going to learn what exactly is Taylor series and how is this Taylor series helping you to approximate different functions. Okay, so the first thing that you have to understand is many functions, let us say like sin x or maybe e power x or log 1 plus x, many of these functions, these can be written as an infinite polynomial expansion around some particular point A. So if you have some particular point A and you want to find approximate value of this function around that point, then there is a way to do that. That is, generally, if you have sin x, what will you do? You would have either simply directly by hearted values of sin x, or maybe you know the graph of sin x, and from that you would be trying to approximate, okay, at this particular point this could be the value. But if you want to get exact value at some particular point A and you want to approximate the closest possible precision, then the perfect way is to use Taylor series for approximation, where it will be an infinite polynomial and this polynomial will help you find approximate value. What I'll do is, first I'll write the mathematical equation, then we'll explain how that equation came up, what is its speciality, and how it is able to approximate different functions. Okay, this would be the best way. What I'll do is, instead of taking sin x or something, I'll take a function f of x. This is a generic function. You can put anything here. It could be sin x, cos x, whatever. So there are certain conditions. First thing is, this particular function f of x, it should be infinitely differentiable around the point x is equal to a. If you want to make use of Taylor series and then do approximation, then the first condition is around the point x equal to a, where you want to find the value of this function, the function should be infinitely differentiable. If it is, then how are you going to find the value of f of x? It is simple. There is a infinite polynomial. So this polynomial is called Taylor series. We'll explain what this is. First, you just see what it is, okay? Around the point f equal to a, I can approximate it like this. First term will be f of a. It will be f of a plus next term is first derivative f dash of a into x minus a plus next term will be second derivative, that is f double dash of a into x minus a the whole square plus third term will be, you can now guess the third term. What will it be? The third derivative. So instead of putting 3 dashes, I will write f3 of a. Understand, it is not f cube, it is third derivative. Okay, f cube of, okay, I missed one thing here, f of a by 1 factorial. Okay, 1 factorial is not required. Here I'll write this by 2 factorial, this by 3 factorial into x minus a the whole cube plus what should be the next term? f4 of a into x minus a the whole raised to 4 divided by 4 factorial and so on. So this is infinite. I am not continuing simply writing next terms. This is an infinite polynomial. So another way of representing the same thing is, this can be written as sigma n is equal to 0 to infinity. How can I represent it? Fn of a. What is this? It is nth derivative of f of a divided by n factorial into x minus a whole raised to n. So this is called as Taylor series. Next question is, what is the speciality of this Taylor series? Any function f of x, if under this condition, that is, it should be infinitely differentiable around x equal to a, Then if you want to approximate the value of the function, then you can use this particular formula, f of a plus first derivative of f of a into x minus a plus second derivative by 2 factorial into x minus a the whole square plus third derivative by 3 factorial into x minus a whole cube and so on. Okay, this is infinite polynomial, keep in mind. Next thing is, this is a Taylor series expansion about x equal to a. Next question is, what is the logic behind this expansion? How am I saying that this particular expansion is allowing you to find approximate value of that function around x equal to a? So then you have to understand what is the significance of each of these terms. So this is what we are going to discuss. So the intuition is something like this. First thing, you took the value of the function at x equal to a. So at x equal to a, whatever is the value of function, that is f of a. That is your first term, right? Then what is your second term? Second term, f dash of a into x minus a. What is the sense of this term? The logic is, you are adding a term that is involving the slope of that function. That is the first derivative. What does this do? When you are taking that first derivative, it is approximating the value just near to a. So now you already have f of a. Now just to the left and to the right of a, if you slightly move, what is the value? That is what the slope is telling you. So if you want to approximate closer, you will add the term involving the slope, that is first derivative, which will give you a bit more of approximation. So that is what this term f dash of a into x minus a is bringing in. The first derivative term is bringing you this approximation. Then if you add the second derivative along with the quadratic term, or then the third term, which is cubic, these ways, if you add the higher order term, then higher derivatives that will refine the approximation. So this is the logic. Because of this, as you add on more and more terms here, it will get more and more defined, and your approximation near a will be more and more accurate. So that is why this particular series is infinite series. If you keep on adding 1000 terms, you will keep on increasing the accuracy. That is accuracy of approximation, that will keep on increasing as you keep adding more and more terms. If you just put the first term, that is also somewhat the value. But this approximation is not as accurate as what you have when you have all the terms. All means there is no particular way of saying it. It is infinite. Whatever be the level of accuracy you want, that is whatever is the level of accuracy for the approximation that you want, accordingly you have to add that many terms that are present in Taylor series. So generally what we do is, we will either take first 2 terms, 3 terms or something, so that we get a very good approximation of what that particular function takes at this particular value x is equal to a. So this is where we generally use Taylor series. So what does Taylor series do? It kind of mimics the behavior of the function locally. Why did I add the term locally? Because locally around x equal to a, how is this particular function behaving? That is what Taylor series is mimicking. If you have some particular function sin x, how is sin x behaving locally around one particular point x equal to a? So mimicking this function is the role of this particular series called Taylor series. Next question is, okay, I'll just show you some of the Taylor series expansions. For example, we talked about sin x and all. So let me just take sin x, e power x and all. We'll see what is the approximation of those functions. Okay, if you take e power x, a way of approximating e power x is around, let us say, x equal to 0. E power x around x is equal to 0. This can be approximated as 1 plus x square by 2 factorial plus x cube by 3 factorial plus so and so till infinite. So this is the approximation of e power x around x is equal to 0. Let us say similarly you want to approximate sin x around x equal to 0. If you want to do that, then it will be something like this: x minus x cube by 3 factorial plus x power 5 by 5 factorial minus x power 7 by 7 factorial and so on. So you understood the pattern, right? Similarly, you can do for other functions as well. In the last lecture, we had seen that we used log 1 plus x approximation. How did we use this in the last lecture? When we had log 1 plus x, same case, around x equal to 0. This is for small x, okay? When mode x is very small, lesser than 1 for sure. Then the approximation we got was in the last lecture, we used this x minus x square by 2 factorial. Sorry, it was x square by 2 plus x cube by 3 and so on, right? So this particular series that we used in the last lecture, that helped us approximate log 1 plus x value in order to find out what is the value of log cos h loss function. Similarly, you can approximate many functions using Taylor series. And the next question is, why are you going to use this Taylor series? Why is Taylor series useful? So first thing, you already know approximation. That is for small x. For small x, often what you do is take just the first 1-2 terms of the Taylor series expansion and you will say, okay, this is somewhat an approximation of this particular value. That is for small x, you would say, let us say sin x is nearly equal to x. So this is not exact, but what I'm saying is this is an approximation. Instead, if you add more and more terms from the Taylor series, then your approximation becomes more and more accurate. And the main usage of this polynomial part is when you want to make some derivations or maybe some tricky derivations, then Taylor series actually makes many of those derivations easier. This is why I actually used Taylor series in the last lecture and then I'm teaching Taylor series here, because now you already know from the last lecture that when we wanted to derive how the value of log cos h loss is actually coming up, we made use of Taylor series so that our cos h function and log function can be easily derived. That is simplifying the actually tricky function. That is what Taylor series did for us. So you can just go back to the last lecture and see how we derived the value for log cos h function. Then you will understand what is the importance of Taylor series though. Otherwise, it would have been difficult for us. Because we had Taylor series, it was much easier for us to do the derivation.